Okay, so let's take a look at 9.11 again. We did this last time, but if you have a molecule like HF, okay, if one of the elements is significantly more electronegative than the other one, it's going to cause the molecule to be polar, right? Which means one side is going to be partially negative. So here, fluorine will be partially negative, and hydrogen will be partially positive. And so there's going to be something called a dipole moment, okay, where one side is more positive and one side is more negative. And so what happens is if you have multiple polar molecules, they're going to rearrange themselves in a way so that the partial negative has somewhat of an attraction to the partial positive. Okay, we learned this last time, or last time. Okay, you guys remember this? All right. Okay, so the dipole moment has a different amount of strength depending on which molecule you're talking about. And so the greater the electronegativity difference, the greater the dipole moment. So the more, the bigger the difference between the two atoms are in their electronegativity, the more there will be a dipole moment. So we learned before that fluorine is the most electronegative element. And so chlorine, bromine, and iodine are all less electronegative. And so if you guys notice, the magnitude of HF is going to be a greater dipole moment because there's a bigger difference in electronegativity between hydrogen and fluorine than the other ones. Okay, so just keep that in mind. There's going to be more dipole moment the bigger the electronegativity difference. Okay, and you guys don't need to memorize these numbers. You don't need to know that HF has a dipole moment of 1.82. What's important is you know that you know the relative dipole moment between the two. So just know that bigger electronegativity difference, the bigger the dipole moment. Okay, you just need to know that principle. Alrighty, any questions about that? Chilling on dipole? Okay. All right, so before we get into, we're going to be talking about more intermolecular forces. We're going to talk about how to draw the Lewis structures for bigger molecules. So we talked about this before, and I have some steps here. But basically, you're going to count up all the valence electrons that are available in your molecule. You're going to make sure that they're all connected, and then you're going to complete the octets for everybody. Okay, so I'm going to do one of these with you guys, and I'll have you guys try the other ones on your own. If you're comfortable doing this, you can go ahead and just ignore me and just try doing 9.12. But yeah, let's get into it. Okay, so here we have CH2Cl2. So we're going to count the valence electrons. So how many valence electrons does carbon contribute? I heard it. Four, yeah. Carbon is the fourth box in the second row. So it contributes 4 valence electrons. How many valence electrons does hydrogen contribute? 1. And so there's 2 of them. So yeah, you would get 2. And then chlorine contributes how many each? 7. So you get a total of 14. So that means CH2Cl2, this molecule right here, has a total number of 20 valence electrons that we can work with. Okay? Okay, so you want to start by counting the valence. Okay, next thing you want to do is you want to kind of rearrange them in a certain structure. So let's start with carbon. Carbon always goes where? In the middle, yeah. Carbon always goes in the middle. We know that hydrogen wants to go on the outside because it can't really bond with anything. Or it can only bond with one thing, sorry. So we'll put hydrogen kind of on the outside. And then chlorine is the most electronegative out of the 3 elements that we have. So it's going to want to make only one bond. And so we'll put it around carbon like that. Okay, so if you made it like an X shape, that's totally fine. But as long as you understand that carbon goes in the middle, hydrogen kind of goes on the outside, and chlorine, it only wants to make one connection if possible, because it's the most electronegative. Something like this should be fine. Okay. Any questions on the structure? Make sense? Okay, now we're just gonna make sure that everybody is connected. So let's connect everybody to carbon because hydrogen can only make one connection, right? Carbon wants to be in the middle, and chlorine, if possible, wants to only make one connection. So everybody connects to carbon. Each line is 2 electrons, so 2, 4, 6, 8. So we used 8, and now we have 12 valence electrons to work with. Okay. Okay, so if we take a look at these elements, let's take a look at which ones are happy now. Hydrogens are happy because they have 2 valence electrons now with those 2 covalent bonds. Okay, is carbon happy? Yeah, carbon is happy because it has an octet. The only ones that are not happy right now are the chlorines because chlorine wants 8. And so we're going to add 2, 4, 6. That's going to get us 6 valence electrons. So we just add 6 each, and then everybody is happy. And we've used all 20 valence electrons. Okay, so that's what this compound is going to look like. Okay, so this is one of the easier ones. The examples that we have coming up, you're going to have to use double bonds or triple bonds, and some of the structures might get more difficult. But if you follow the rules that we went over, eventually they will all work out. I won't give you any impossible compounds. Okay. All right, so I'll give you guys about maybe a minute or two to try 9.13. I want you guys to find the Lewis structure for HCN. Yeah, feel free to work with the person next to you, and then we'll go over it in about 2 minutes. Okay, so HCN, the valence electrons should have been pretty easy. You got 1 from the hydrogen, 4 from the carbon, and you got 5 from the nitrogen. Okay, that's going to give us a grand total of 10 valence electrons to work with. Okay. Now we know that carbon likes to be in the middle, so we'll put carbon somewhere in the middle. H likes to be on the outside, so I guess something like that. And then we got nitrogen. Probably wants to be alone because obviously it's the most electronegative. Okay, so something like that. If you want up and down, diagonal, doesn't really matter as long as they're somewhat like that. Okay. Okay, let's make sure everybody is connected. So we're going to connect hydrogen, carbon, and nitrogen. So 2, 4. So we got 6 left to work with. Now, let's start by putting it on the most electronegative one. So we're going to put 2, 4, 6 on nitrogen. And so nitrogen is happy, hydrogen is happy, but carbon is sad, right? Because carbon needs an octet. And so what's going to happen is carbon and nitrogen need to share. So we're going to share 1 right here. If we do that, nitrogen's happy, but carbon only has 2, 4, 6. And so it's going to force nitrogen to share 2 more. And so we got a triple bond right here. And that's what's going to make carbon happy. So this is HCN. Okay. So all you got to do is move the electrons around until everybody has an octet and they're happy and ready to go. Okay. Sounds good? All righty. Let's move on. Okay, we'll skip 9.14. I'm going to have you guys try 9.15. Now, this one's a little bit trickier because if you guys notice, this is an ion, right? So that means that we're going to have to change something about the valence electron count. So think about what an ion means in terms of electrons, and that'll help you with the count. So I'll give you guys 2 minutes to try that one as well, and then we will go over it together. All right? Okay. All right. So let's go over this one. So for this one, which one is gonna be in the middle? Yeah, Burr is gonna be in the middle. Okay. The reason why is because bromine is the least electronegative, right? And so it's gonna want to be in the middle, and the oxygens are more electronegative, so we're gonna put them somewhere on the outside. So it doesn't really matter how you organize it. We'll do it like this for now. Okay. So we got 3 oxygens, 1 bromine. Chilling? Okay. Okay. We're going to connect everybody together. So oxygen, since they're the most electronegative, probably not going to want to share. So we're going to connect everybody to bromine. That's 2, 4, 6. That's going to get us down to 20. Okay. Now, everybody wants to get an octet. So let's start with the electronegative ones because they're the ones that are most selfish for the electrons. So we're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh, I guess the octet does work. My bad. So we used 18, so it's gonna get us to 2. And then we're gonna put 2 more right here to complete the octet. Sorry, guys. My brain is busted. Okay. Yeah, this is right. Sorry, I lied earlier. And then make sure you put the brackets and the negative sign. Okay, now, if you want it to be as accurate as possible, technically these electrons push electrons away, right? So you would want to make it kind of like this. You want to spread the oxygen out like this and put it something like this. You can either do it like this shape or an X shape. That's the most accurate. But as long as you got the correct bonding and the lone pairs on the right spots, you should be good. Yes. Br contributes 7 valence electrons, but it still wants to form an octet. No. Okay, so let's start with the initial count, okay? So bromine has 7 valence electrons. That part makes sense? Okay, oxygen contributes 6 each, and there's 3 of them, so that's 18 total. And then you see how there's a minus sign? That means we need to add 1 more electron because it gained an electron. The minus sign means there's 1 more electron. Is that the part that was messing you up?
Wait, but where did the 7 go?
So the 7 is only about, it only talks about how many electrons that it contributes to the whole molecule. Yeah, it doesn't mean it wants 7 at the very end. It still wants a complete shell. You know how everybody wants to form a complete shell? So yeah. No. Yeah. Mm-hmm. Yeah. All righty. You guys good? Okay, let's move on. All right, now we learned about the octet rule, but if you guys take a look at some other Lewis structures, you're going to notice that there are multiple ways to draw the same molecule. So for example, we got carbon dioxide, CO2, and if you look at the one on the left and the one on the right, you're going to notice that both of them are viable structures, right? The one on the left, everybody has an octet. The one on the right, also everybody has an octet, right? However, there is a better structure, and we're going to be learning how to determine which compound has the better structure. Okay, and the way that we figure out which Lewis structure is best is we use a equation called formal charge. Okay, so make sure you guys copy this equation down. Formal charge. Okay, and formal charge basically is equal to the group number. Okay, basically what group it is in, which column it's in, minus the number of covalent bonds on that atom, minus the number of lone pairs that it has. Okay. Group number, which column it's in. Yeah, basically how many valence electrons does it contribute? Yeah, so if you want to write this, first one, group number as number of valence electrons it contributes. Okay, you could think of it like that. Okay, so for example, carbon would be 4, nitrogen 5. Yes. Okay. Yeah, exactly. Okay, so that's the equation. And we can use this equation to figure out what the best structure of a molecule is going to be. Okay, now there are a couple things you need to keep in mind with this formula. It's right here, the 2 steps I have. The first is that the dominant Lewis structure, basically the one that it wants to be, is the one where the atoms have a formal charge of 0. Okay, so if everybody is 0, that's automatically the best structure. Okay. Also, the dominant Lewis structure is the one where the more electronegative atoms have a negative formal charge. So in the case that not everyone can be 0, we want the electronegative ones to have a negative formal charge. Okay, so those are the 2 things you need to keep in mind. Okay, the best one is the one where everyone is 0, but if you can't get everyone to 0, then whichever structure makes the electronegative atoms have a negative formal charge, that's the best one. Okay. Okay, so it's actually a lot of work because you need to find the formal charge of every single atom in that molecule for multiple molecules. Okay, so a little bit annoying. Okay, so I'm gonna do the first structure with you guys, and then I'll have you guys do the other two on your own. But yeah, let's figure out of these three Lewis structures, which one the best structure is, okay? So let's start with nitrogen, okay, on the far left. Okay, we'll do this one together. Okay, so if we take a look at the formal charge of nitrogen, so I'm gonna write Fc of nitrogen, okay? First thing that we want to do is figure out the group number. So what's the group number of nitrogen? 5, yeah, 5. It contributes 5 valence electrons. How many covalent bonds does nitrogen have? 1. Yeah, it's only one line, so -1. And how many lone pairs does it have? 6, yeah, 2, 4, 6. So the formal charge on this nitrogen, we're going to calculate by doing 5 -1 -6. So the formal charge on this nitrogen atom is -2. Okay. Make sense? Okay, pretty easy formula. All you got to do is make sure you count them up correctly. Okay, let's do the formal charge of carbon in the middle, okay? So Fc of carbon. Okay. How many valence electrons does carbon contribute? 4. Okay. Now, this is the one that might be a little bit tricky. So the number of covalent bonds, basically how many lines it is connected to it. Okay. Yeah, you got 4.
So it's
Yeah, so you count triple as 3. Yeah. And then if you look, how many lone pairs does it have? 0. So 4 minus 4. So the lone pair, or not the lone pair, the formal charge of this carbon is going to be 0. Yes.
what do you have multiple carbons and multiple nitrogens? How is
So this formal charge, we usually use it with one where there's only one in the middle. One molecule, one atom in the middle.
But like if it was like NH3, then and how would you describe each hydrogen's formal charge?
It would be 1 for the group number, 1 for the covalent bond, so 1 minus 1, and 0 lone pair, so 1 minus 1 minus 0 is 0.
Yeah, but I'm saying like you have formal charge hydrogen and you also have formal
Charge for the nitrogen as well. Yeah. Okay. And then last one, let's do the formal charge of sulfur. Sulfur contributes how many valence electrons?
6.
6. Okay. How many covalent bonds does sulfur have? Not 2, 3, yeah. Because it has the triple bond 1, 2, 3. And then how many lone pairs does it have? 2. So our formal charge for the sulfur is going to be +1. Okay, does that make sense how to find formal charge? Now, just finding the formal charges of the elements on this molecule doesn't really help us because we need to compare it with the other ones, okay? So I'm going to have you guys pick a partner, pick someone next to you, and you guys are going to split the molecule. So choose one partner to do the middle molecule, the structure, and choose one person to do the rightmost structure. If you guys don't want to, what's up? Yeah, do the exact same thing. And then after you guys finish finding the formal charge, talk between the two of you and try to figure out which one of these 3 structures is the best. Okay, so I'm going to give you guys maybe 3 minutes to calculate the formal charge, compare answers, and figure out which structure is best. Move on. Okay, so I'm just going to give you guys the formal charges for everything. If I get something wrong, please let me know, because obviously I'm making a lot of mistakes. -1 for nitrogen, 0 and 0 for carbon and sulfur. Good?
You just raise their grade like.
Oh, no, I'm good.
Every single time you make a mistake.
How about this? Every time you point out a mistake I make, I lower everybody's grade. Okay, that way I preserve my image as being perfect. Which is obviously true. Yeah, I don't really. Hey, it's your grade, not mine. Okay, so I got 0, 0, -1. Good? Okay. So we gotta figure out which one of these is the best structure. Now, none of them are 0 all the way through, so number 1's not going to work. So now we got to figure out what the most electronegative one is, and that one preferably will have the negative charge. So between the 3 elements, which one is most electronegative? Yeah, nitrogen is the most electronegative, and so we want nitrogen to be negative, have the negative formal charge, and so that means the middle structure will be the best structure because nitrogen, the most electronegative one, has a negative formal charge. Okay, so that's how you would use formal charge.
Is it better for all zeros, like number 1, the first?
I don't want
Yeah, so you want to make sure that most of them are zeroed out if possible, and then the negative only goes on the electronegative. Also, yeah.
Whatever you possibly say, the last one, all the first 0. Like, then which one?
If it, like, let's say hypothetically this was 0, yeah, then this is the best one.
Okay.
Yeah. Also, this one doesn't work because if you look between carbon and sulfur, sulfur is more electronegative than carbon, and yet it has a positive, a formal charge, and so that's not a good way to do it either. Yeah. I'll get to you after. If you look on the periodic table, it's the most up and to the right out of the 3. So you got carbon, nitrogen, sulfur. So nitrogen is the highest, and so that means it's close. It has the fewest amount of shells compared to sulfur. So it's more electronegative because it has less shells. So the valence electrons are closer. And between carbon and nitrogen, nitrogen has more protons, so it holds the electrons more. Yeah. In my experience, you'll have one of them, or like the most electronegative one, have negative, and then 0, 0, 0. That's usually how you're gonna see it. Yeah. Yeah, good question. Okay, any other ones? All right, let's move on. Now, we talked about formal charge to figure out the best structure. There's also something called a resonance structure, okay? So if we take a look at a molecule that has, let's say, the same elements in it, okay? So something like ozone, O3. Okay, you can draw it 2 different ways. And if you look at it, it might just look like mirror images of each other, right? Okay, however, we know that every single element matters, right? And so let's make sure they have the unique name that they deserve, okay? So I'm going to name this one 1, 2, and 3 to show I care very much about them, okay? Okay, we're going to call them 1, 2, 3. So if you guys notice, we can draw it like this, where oxygen 1 and 2 have a double bond, right? But you can also draw it in a way where oxygen, the second one, and the third one have a double bond, right? They are both correct. However, this isn't an adequate or a sufficient way to explain this molecule because neither of these is going to be the best structure per se, okay? And so we have to draw something called a resonance structure. So in real life, what's going to happen is it's going to look more like this. You're going to have your 3 oxygens, okay, and they're going to be connected like this. But instead of a double bond between either of them, they have something called a 1.5 bond, okay? And we use that to describe, and we can draw it like this, okay? And this is something called a resonance structure. And what it does is it tells us that the 3 oxygens, it's not like you have a double bond and a single bond. Instead, the electrons are distributed evenly throughout, and you get something kind of like a hybrid bond, where it's about in between the distance of a single and double bond, okay? Okay, so the electrons are spread out between the 3 of them rather than having a double and a single. You have something where they're spread out between them. Okay. And the reason why we do this is because Lewis structures are just drawings. They're models that we use to kind of show what's happening in real life. But every single model fails in some way, right? And that's why we need to use resonance bonds to represent it. Yeah. No, so you have 2 options. You could either draw it like this to show that it's a resonance structure. But honestly, if you just drew one or the other, that's totally fine because it demonstrates that you understand how the octets work. Yeah. Unless they specifically ask for a resonance structure, you can draw it one of the traditional ways. Okay, good question. Yeah. Mm-hmm. Oh, good question. So it would be more like, usually we don't draw the lone pairs, but it would be kind of something like this. Yeah, because the electrons are shared between like that. But again, you don't need to draw the lone pairs, especially when you have resonance structures. Okay. So let's draw the resonance structure for formate HCO2 minus. So we're going to draw the two different resonance structures they can make. And then after that, we'll draw the one with the 1.5 bonds. Okay. Okay, so we'll do this one together, and then I'll have you guys try one on your own. Okay. Actually, no, we're just going to do one together. Okay, so let's count. So hydrogen contributes 1 valence electron. Carbon contributes 4 valence electrons. And then 2 oxygens will give you 12. And then the negative sign will give you 1. So this will give us a total of 18 valence electrons. Okay. So actually, I'm just going to have you guys try it on your own. See if you guys can draw both resonance structures. And then see if you can also draw it with the 1.5 bonds. Okay, so give you guys 3 minutes to do that for 3 different structures. And then we'll go over it together. Okay, so for your structure, you guys should have carbon in the middle, got hydrogen, and then the oxygen spread out. And then we are going to start by connecting them together. So we're going to go 2, 4, 6. That's going to get us down to 12. And then what we're going to do is, I'm going to call this oxygen, call it oxygen 1. And we'll call this guy oxygen 2. Okay, carbon and oxygen 1 can make a double bond. That'll get us down to 10. And then we'll have to put 2 here, 2 here. That'll get us to 6. And then we'll put the 6 right here on oxygen 2. Okay, so that's one way that we can do it. And then I didn't draw the brackets, but it's because I don't want it to get too cluttered, but make sure you put the brackets, okay? I'm not going to do it here just because it's going to get cluttered as we draw more structures. But yeah, you're going to want to put the brackets and then minus, okay? Everybody good with the first resonance structure? Okay. Now, we can also do it another way. Basically, the mirror of that, where you have carbon, hydrogen, oxygen 1, and oxygen 2. But instead of forming a double bond with oxygen 1, carbon is going to form a double bond with oxygen 2. And then from there, everything just flips. You'll have 4 lone pairs, and then 6 lone pairs. And then we got that. So these are the 2 resonance structures of formate. Yes. We don't have enough electrons to do that. Or because if you do that, so yeah, because if we do that, yeah, it's gonna violate carbon's octet and carbon gets too crowded. Yeah, good question though. What's up?
So those wouldn't occur naturally, like you wouldn't get those.
So in real life, none of this is real. Yeah, there's no, yeah, these are just pictures and models that we use to understand, right? The phenomena. But in real life, resonance is the better way to think about it. Because remember, electrons are always moving, right? And that's kind of what I wanted to get at with resonance structures. Electrons are constantly moving. So let's take a look at this resonance structure right here. In this double bond, we like to think of it as there's 4 electrons working there, right? In the single bond, we like to think of it as 2 electrons working there, and then vice versa for the other resonance structure. Okay, but in real life, it's not like these electrons are pinned between these atoms. Remember, electrons are constantly moving around. So it's not as if when we have a bond, it doesn't mean the electrons are stuck there. They're constantly moving around throughout the molecule. And so it's not like they're stuck like this. And that's why resonance is more helpful in understanding the real, how it works in real life, because the electrons are constantly moving. And yeah, there's going to be 2 electrons most of the time here. But in between the 2 oxygens, the 2 electrons that form the double bond, they're going to go back and forth constantly. They're going to go back and forth between the two oxygens and the carbon. And that's why it's going to tend to be a 1.5 bond, where it's shorter than a single bond, but it's longer than a double bond. Yeah.
So if they're always moving,
Mm-hmm.
electrons are always moving.
Yes.
Then how are the molecules staying like together?
Yeah, so it's probability. So they tend to be in these positions where they can keep the atoms bonded together.
So it's less of like bonding and more of sharing.
Yes.
Supposed to be together.
Yeah. Yeah, and so this is a problem when we're trying to understand it, right? Because there's nothing that works in our world that we can refer to, right? It's not, we can't like pin it to anything in our macroscopic life, and that's why it's very conceptual. But yeah, these electrons are constantly moving, and so because of the sharing, that's what causes them to bond. Yeah, just know every single model is imperfect. This is the limitation of the Lewis structure model, right? And so yeah, that's just kind of the limitations. Yeah, what's up, Sammy? Oh, we'll go Sammy and then we'll go back to you. Yeah.
Also, are they all three?
So this would be so these we would consider, so yeah, that's a good question. So in terms of nomenclature, the naming, these are the two resonance structures. Okay, so this is how we would draw the two resonance structures. Thank you. To two resonance structures of formate, and then this would be the one. This we would just call this the resonance structure because it combines the two resonance structures together. That's how we name it. And the naming is very weird. So if you see 1.5 bonds, we call that the resonance structure. If you have the two options or three options, we would call that the three resonance structures. Yeah. Okay, good question. Yeah.
Are resonance structures considered like an offshoot of Lewis structures, or they're like?
Yeah, it's like a more specific way of Lewis structures.
But it's
Yeah. What's up?
you have to draw this on the
There's usually a resonance structure question.
Right.
Sometimes. Both.
Okay.
Yeah, so there's questions where they're like, hey, draw the three resonance structures of this molecule, just like we did here.
Okay.
And then some where they give you the three resonance structures, and then yeah.
And then will this be on our
Maybe. Anything is fair game, guys.
Sure.
Anything.
one question for that one exam that everybody failed?
Oh yeah, the ring.
Yeah, you did.
Yeah. All right, let's move on, guys. Okay, so this is the last resonance structure, and this is actually one that was from an AP test. So speaking of AP test,
So that was on the-
yeah, so I want you guys to take a look at these two compounds, SO3 and SO3 2-. And I want you guys to draw the structures and then figure. Oh, my bad, I can't count either. Okay, but I want you guys to figure out which one has a shorter sulfur oxygen bond. Okay, was it? Oh.
Well, I have my turn.
But anyway, I'll give you guys about 3 minutes to try it out. Talk with the person next to you. See if you guys can write an FRQ style response. Again, don't humanize these molecules. They're not human. They don't feel anything. They don't want to do anything. They're not happy. They're not sad. We want to be very unemotional when we're writing about them. Okay, so let's start with SO3 2-. Let's talk about the ion first because that one's a lot easier to work with. It's gonna look like this. You got an octet on everybody, and then everyone has lone pairs. Everybody good on that one? Okay, so this is going to be the structure for the ion, but let's take a look at the neutral one. Now the neutral one, we got a double bond between, and I'm gonna name them again. We got oxygen here. We'll call this oxygen 1, oxygen 2, and oxygen 3. Okay, so you can draw multiple different structures depending on which one you want sulfur to form a double bond with, right? So sulfur can find the double bond with oxygen 1. Okay, but it's also equally valid to form one where it has a double bond with oxygen 2. I'm gonna get rid of the lone pairs for the sake of simplicity. Okay, so yeah, your lone pairs would change if you put a different double bond. Okay, and sulfur can also form a double bond with oxygen 3, right? So any of those options would be fine. You can make one with 1, 2, or 3. Okay, and so what that means is it has a resonance structure where the electrons are shared between all three of the oxygens and the sulfur. So this would be the resonance structure for SO3, okay? And then if you guys ever do this on an exam, please don't put the numbers. Don't do 1, 2, 3. Yeah. Okay, so this will be the resonance structure. But if you drew any of the 3 resonance structures, that's totally fine. If you drew all 3, even better. Or you can do the 1.5 bonds, yeah. So you can, but I wouldn't recommend it. Just because the counting gets very annoying. Like, how do you count the number of electrons in these? Like, it gets a little bit difficult, right? And so I would recommend not doing the lone pairs for resonance structures. Yeah. Yeah, any of the bond oxygens is fine. Yeah. Okay. So the point of the question is not to draw these structures, but to ask or to figure out which one has the shortest SO bond. Now, if you take a look at the sulfur and the oxygen here, what type of bond is that? Yeah, this is a single bond. Okay, it's one line, very easy, single. Okay. But if you take a look at these sulfur and oxygen bonds, what type of bond is this?
Like 1.5.
Yeah, 1.5. Okay. And since it's 1.5, we can use the pattern that we learned before. We learned that there's a distance difference between single, double, and triple. Which one of the 3 is the shortest bond? Yeah, triple is the shortest. So as you have more bonds between the atoms, the shorter they become. So which one of these is shorter? The 1.5 or the single? Yeah. So that means SO3, you would answer the question as SO3 has a shorter SO bond. Okay.
So it's still 1.5 or this number reach.
No, it's 1.5 still. Yeah. And it's because the electrons are moving in between them. They're shared equally. It's not as if they're, yeah, they don't belong to anybody. Yeah, go ahead. Actually, this is a good time to take a break. So I'll get to your question, but I'll give you guys a 5-minute break. But yeah, what's up?
Like the less repulsion. Not like exclusion.
What do you mean less repulsion?
It's like there's less electrons.
Oh, you mean total contributed electrons, 24 versus 26, right? Yeah, so that wouldn't work because the main difference in their structure isn't the repulsion, but it's how they're shared between each other. Yeah. That's a good observation though. Yeah. But that wouldn't work for this one. That's usually for when you have it in like a single atom. Yeah. So the one exception we know to the octet rule is hydrogen, right? Hydrogen only can hold 2, so that's not an octet. But there are some other elements that don't follow the octet rule. Okay. The first example is going to be when a molecule has an odd number of electrons. Okay. So we got NO. Okay. NO is going to have an odd number of electrons because nitrogen gives you 5. Oxygen gives you 6. And that means we have a total of 11 valence electrons to work with, right? So obviously they can't both have an octet if we only got 11 electrons to work with. And so I want you guys to take a look at the 2 possible structures for NO. And I want you guys to just think about which one of these is going to be dominant. Okay. Now, there's an easy way to think about this and a hard way to think about this. Okay. And I want you guys to see if you guys can figure it out the easy way and the hard way. So there's 2 explanations you can give. They're both equally correct. One requires less work though. So I'll give you guys a minute to think about that, try it out, and then tell me which one is more dominant. Okay, so like I said, there are 2 ways to do this, easy way and hard way. Does somebody want to volunteer one of their explanations? Yeah.
Which one is more electronegative?
Yes. The easy way is which one is more electronegative. So if you take a look at these, which one is more electronegative, oxygen or nitrogen? Yeah. Oh, I am the most electronegative. Okay. So since oxygen is going to be more electronegative, does it want more electrons or fewer electrons? Yeah, more. So that means this one is going to be correct because oxygen is more electronegative. So it wants more electron. Yes.
It doesn't just want to, like, it's full.
It does, but in this case, nitrogen can't get its full shell, right? So you got to choose which one gets the full shell, and it's gonna be the one that's more electronegative. Yeah.
On the test, on the, like, say, like, oxygen is more selfish.
No, you definitely won't get points for that. Remember, they don't have feelings, okay? Just like you guys, no feelings. You want to be very you want to use the vocabulary you learned in this class. So instead of saying oxygen is stronger, you would want to say oxygen is more electronegative. The reason why is not because it's, I don't know, because it's more selfish, but it's because they have the same number of shells, but oxygen has more protons. There's more attraction to the nucleus. Just very as descriptive as you can get. Yeah. No emotional language. Yes. Yeah, what's up? No, you don't want to say once more. You want to say oxygen is more electronegative. You can say oxygen has a greater affinity for electrons than nitrogen. That works. But it can't want anything because it doesn't have, it's not sentient, right? It can't want nothing. Yeah.
I didn't try it, but do you use formal charge?
Yes, I was gonna go over that.
It would be worth it, but like a rate, like an extra note for this one, and say that electron or not, that's more like the when you take it.
Yeah.
Oh, do you want to stick to the electromagnetic?
No, you don't need to do that. Okay, the other way that you can do this is, like Robbie said, you can calculate formal charge, and I did that for you, so you don't have to. But the formal charge of nitrogen here will be 0. The formal charge of oxygen here will be 0. But on this one, you'll have a -1 on the nitrogen and a +1 on oxygen. So obviously, this one, even using formal charge, is the better structure because they're both zeroed out. This one makes no sense because the less electronegative one is negative, and the more electronegative one is positive. So this is poo-poo, no good. Okay, yeah.
Does it happen very often when we have exceptions to the?
You'll rarely see it. Yeah.
Yeah, same.
Yeah. You'll rarely see one with an odd number of electrons. This is actually called a free radical. And this is very not good. It's very unstable. That electron likes to shoot out. Usually we see free radicals in areas that have been affected by radioactive decay. So like places where there have been nuclear accidents, see a lot of free radicals because it damages DNA. Yeah. But anyway, that is nice. Okay. The next one is atoms that have less than 8 valence electrons. So we know 2 exceptions, and the first one is hydrogen, right? Hydrogen holds 2 valence electrons because it is teeny tiny. It can't hold any more. The next exception that's notable is boron. Boron is also teeny tiny. It's 5 protons, and so boron can either hold 6 and be happy, or hold 8 and be happy. Okay, either works.
Why?
Because it's teeny tiny. It's teeny tiny, but it's not so teeny tiny it can only hold 2. It can either hold 6. They're metals, so they give away. Yeah.
What about carbon?
Carbon is helium's a noble gas, so it doesn't want to react. Boron's a metalloid, so it has features of a metal and a non-metal, so it could either form an ionic bond or a covalent bond. Here we're talking about covalent bonds, and that's why it can do that. Yeah.
Is there any other ones?
No, the notable ones are hydrogen and boron.
Okay.
Yeah. Those are the only ones you'll really need to know. Okay. Okay, and then the other one, and this is the big group and the most important one to keep in mind for exceptions, and it's molecules where atoms can have more than 8 valence electrons. So just like how small atoms can only hold 8, big fatties can hold more than 8. Okay. Sorry, I am fat shaming these elements because they have no feelings, like I said earlier. Okay. And molecules that have central atoms, usually it's going to be the atoms in the middle of the molecule. They're called hypervalent, which means they can hold more than 8 valence electrons. Okay. Now the key thing to note here is that the central atoms from period 3 and below can hold the stable hypervalent elements. Okay, so it's only ones that are on the 3rd row and below. Okay, so if we take a look at the periodic table, it's going to be basically from phosphorus. Anything bigger than phosphorus can be hypervalent. Okay, so the second row can never be hypervalent, okay? They're not gonna hold more than 8. They're still too small. But phosphorus is where it starts getting big and it can hold more than 8 valence electrons. Okay, so yeah, including phosphorus. So the notable exceptions are gonna be phosphorus, sulfur, bromine, sometimes chlorine. Chlorine is pretty electronegative though, so it really doesn't like being in the middle, unless it's bonded with like fluorine or something like that. But these are the 5 ones you'll see the most: phosphorus, sulfur, bromine, iodine, and xenon. Okay, and they can hold either 10, sometimes 12. Yes, 10 or 12. I was gonna say you'll never see one bigger than 12, but yeah, you'll rarely ever see one more than 12. Yeah.
I thought since xenon was noble gas.
Yeah, so xenon is in the noble gas category, but because it's so big, the valence electrons are so far away from the nucleus, it can still form bonds. Yeah. So as things get bigger, like once we go to the extremes, the general rules that we follow don't apply anymore. So xenon actually can form covalent bonds. Radon can as well. So anything, basically the biggest ones.
Okay, next one.
I'm not, that one is so unstable it breaks down, so it cannot form a covalent bond. Anything bigger than uranium is man-made. So if you look at the things at the very end, like 113 and up, those are synthetic. They exist for less than a second and then they disappear.
How did they?
How do they make it?
Yeah.
So it's actually pretty big brain, but also very caveman at the same time. They'll usually they'll have like uranium, and then they'll shoot a bunch of like calcium atoms. And so if you notice, uranium is 92, calcium is 20, and they're gonna shoot a bunch of calciums until they're forced to combine, and then they'll have the combined molar mass. So it's 112, and that's how you would make. Yeah, oob. Yeah, so that's how they do it. They literally just shoot nuclei into the other nucleus until they combine, and you can probably tell that's very unstable, right? Yes, they force them together because for a split less than a second, the nucleus fuses together and it stays together for like less than a second, but it's still fused together. Yeah. You guys okay?
That they like that.
They don't care because they don't have feelings. So Jade, you're so thoughtful. You're thinking about these elements. No, but scientists don't care. Okay, so we are going to do one example and then we'll finish up for today. I want you guys to take a minute to draw the structure of XEF2. Okay, XEF2. And if you guys remember, this was on the exam. XEF2. What is the Lewis structure of XEF2? I'll give you guys 2 minutes to do that. For the day. Okay. How many valence electrons does xenon give us? 8, yeah. Okay. What about fluorine? 14 for the 2 of them, 7 and 7. So we got 22. Okay. So which one of these goes in the middle? Yeah, xenon, because it is much less electronegative. And then fluorine goes on the outside. So we got to connect them. Okay, and that's going to get us to 18. Okay. Now, we want to make sure the fluorines are happy because fluorine is very selfish. It wants all the electrons, so we're going to put 6 on both of them. Okay, so 6 and 6, that's 12. And we'll be left over with 6. Now, we have leftover electrons now, and we can't put them on fluorine because fluorine is too small to accommodate for all of them. And so we have to put it on the big xenons. We're going to put 2, 4, and 6. And that is going to be your structure for XEF2.
Okay, now let's go.
All righty, guys. So that's going to be it for today. And yeah, good work, everybody.